Hi all, today we will try to implement FIR filter and fixed point. First we will see like FIR filter design, like FIR filter how the floating point code is implemented in C. With that we will see, like DLL and implementation we will see. Then we will understand like floating point representation, what actually is floating point representation is. Then we will try to motivate like why we go for fixed point. So then we will see fixed point representation. So like what are Q formats, what is Q15, what is Q14, what is Q13, like what are the formats, like how to convert a, and then we'll see how to convert a float value to fixed point conversion, how to do. Then you will see fixed point arithmetic, like how to add two fixed point numbers. So what happens if you multiply two fixed point numbers, what will be the output result, how what will be the Q format of the output. So all those things we will see, and then you will see a practical example, like we will try to generate the filter coefficients for a given specification, like cutoff frequency and passband attenuation and passband ripple and stopband attenuation. All those things we will give as a parameters to the Python library, and we will get the filter coefficients. We will get actually 13 filter coefficients you will get. So those will be in float. We will try to convert those filter coefficients into fixed. Also the input that is coming to this FIR filter is also in float, that also will convert into fixed. So how to convert these things like coefficients into fixed floating point, they will get from the Python library, right? So that we have to convert to fixed point, and then also input also you have to convert to fixed point, and then run each frame and get the output. And then the output of the FIR filter will, in the fixed point, we will compare with the floating point output using RMSE, root mean square error. Root mean square error means nothing but, so if you see here, each sample, if you see floating point sample, let us call it X, then and fixed point sample, let us call it Y. So each sample, like each sample wise we will subtract them, like 0th sample we'll subtract, we'll square it. So like this, we'll square it, and this we will do for all the values. Like if you say this is K, so for all samples we will do this. So sigma will come here, sigma over all samples, like also over all K. So all K will do that, and then we'll take a square root of this. Remember, then they divide by this entire thing, we divide it by the number of samples that are there, number of samples, that is the mean that you are taking, number of divided by number of samples, then this entire thing will take square root of this. So this is what we call as RMSE. So if it is very small, then we say that our fixed point implementation is working fine. So like around 60 to minus 70 dB is okay. So like a fixed point implementation is working fine, like that we can say. So like floating point value, we'll get, this is the floating point value. We'll fixed point also will convert into float, and then we'll give this here, and then we square, and then overall signals, and then number of samples will do, and then square root will take, that will get the RMSE value. So if it is very low, then we can say that the fixed point implementation is working properly. So that's one idea. So RMSE we will use, so to check whether our outputs are coming properly or not in fixed point case. So now coming to next, what is there is why we go for FIR filter is, it is linear phase. Linear phase in the sense that what I mean by linear phase is, so if you see any filter, it will be of the form h of z. Okay, h of z, magnitude h of e to the power of j omega, magnitude part, and then there will be some phase part, h of e to the power of j omega, then that is the phase part. So what I mean by linear phase is, this phase part is there, this angle h of e to the power of j omega will be of the form e to the power of minus j omega n naught. So it is a linear function of frequency. So if you see omega n naught is a linear function, right? Linear function of omega. So that's the case. So the phase will be like this. So when the phase is like this, what happens is, so if you take for example, I take an, okay, don't. So phase is like this. Now if at all we are if x of e to the power of j omega is the input, then if I multiply with mod e for j omega, this only mod if I take, let us call this output as y1 of e power j omega. Okay. So again we have to multiply this with the angle h of e to the power of j omega. Okay. That one we have to do. Okay. So that one y1 e to the power of j omega, if it is a linear phase, what happens? This comes out to be e to the power of j omega minus j omega n naught. So we know from properties of dt of t, this is nothing but y1 of output will be like in time domain, it will be y1 of n1 minus n naught. So this is the output. So what happens is when the linear phase is there, the waveform is preserved, output waveform is preserved. If the output is like triangular, then the output waveform will be preserved, but only delay will be there. So what I mean to say is, so if at all the output is supposed to come like this, triangular at 0 location, because of linear phase, if you are maintaining, then it will come like this at n naught. So the shape of the waveform is maintained if you are using linear phase. So that's the reason why FIR filters use linear phase. And how will you get linear phase is in the sense that if at all the number of coefficients m is, say for example 3, then the filter should be like this. So if this is 1, this should be 1, this should be 2. Okay. Or another thing is this can be also like this also, like 1, this is 1 means this is minus 1. This is a symmetric case and this is an anti-symmetric case. So like this, if it is there, then there will be linear phase will be maintained. And if at all this m is, say for example m is say 4, then the output should be like this. This should be same, this should be same. So if you put a mirror here, this side and this side should be mirror images. That's when the linear phase is maintained. And we have to design FIR filters like this, like the symmetric case like that we have to design. So that's the case. So why understand linear phase, you know that waveform shape is maintained. Another thing is there is no feedback in the case of FIR filters. So the output depends only on the current and the past inputs. Okay. So only inputs it is depending. So there is no output. The output dependence is not there in the case of FIR filter. So output, if at all there is some noise is creeping into the output, that will not be reinforced in the case of FIR filter, and the filter will not will not give some noise kind of some peak, like big values it will not give. So it will be like a summation of some number of terms. So it will be like bounded by some value. So that's the reason why FIR filters are always stable. So if you see what I mean to say is, if you see FIR filter equation is nothing but sigma you will put, and then x of n minus k into h of k. H of k you will put. Okay. This k varying from 0 to m minus 1. M is the filter order. So these are only some limited number of terms that we are multiplying and adding. So this is going out of bounds is not possible. Only when the output, if at all, if it depends on the output, then if the output is going more means it will keep on adding and then it will might get bigger. But in this case, it is not possible like that. So that's the reason why FIR filters are stable. So that's one thing. And next, this is the just now I showed you, right, that this is the equation. So h of k, x of n minus k. H of k is the filter coefficient, h of n is the filter input signal, y of n output signal, m is the number of filter taps. Now in order to implement this, there are various ways. One is direct convolution, like multiplying x h of n with x of n minus k, and then so for each output, how many multiplications we have to do? M multiplications we have to do, and m minus 1 additions we have to do. So for each output calculation. So that's the case. So direct evaluation, direct convolution we can do, that will be order n minus order of n into m, and order with the complexity. There are other methods also, like overlap add and overlap save, where you will use FFT. So FFT is much faster. So like input we will convert into FFT, and the filter coefficients also will convert into FFT, and then you multiply the FFT element wise, and then we will take the IFFT of the output. Then we will get the convolution output. So that's one way. So like in those cases, overlap and add and overlap save are used. So one more thing is, we will divide the input into blocks. So we don't process the entire signal. We don't wait for the entire signal to come and then process it. The reason being, if the signal is coming from some place, for example, so some speech signal is coming. If you wait for the entire signal to come, maybe the signal is coming for 1 hour. So if you after 1 hour you start processing the signal, you can process it, but it will take some. But after 1 hour only, the receiving person will be able to listen to the speech. So if you want as the speech is coming, if you want the other person to listen, then we have to chunk it into blocks and then process them. So like what processing will do, like speech is coming. So for example, like if you want to, speech is coming, if you want to make the pitch of the speech, like if male person is speaking, if you want to convert the pitch into female, then some processing, FIR filtering or something like that we have to do. So that FIR filtering we have to do in blocks, instead of waiting for the entire signal, 1 hour signal to come, and then after that changing the pitch of that, we will take blocks of, say for example 10 milliseconds, and then convert that into pitch of female, and then play it to the user other end. So like continuously you will be getting the signal, like every 10 milliseconds you will be getting a signal. So first 10 milliseconds there will be a lag, after that you will get continuously signal. So first 10 milliseconds why you will get, because you have to buffer first 10 milliseconds, then only we can process on that 10 milliseconds. So that's one thing. So now we will see the FIR filter implementation using delay line. So how to do that we will see now. So first we have to see the code of FIR filter. So this is the code of the FIR filter. So let us take for our case, if you see here in this example, I have taken frame size to be 4 and filter length to be 2. 2 elements are there in the filter and 4 in the frame. Okay. So that's the thing. So like in our case, frame size is 4 and filter size is 2. That's what I have put here. Filter size is 2 and frame size is 4. So now delay line will be of size filter size -1. So this is 2 -1, 1 will come. This is already 4. So 5 is the delay line size. Array size is 5. Okay. So that's what I have depicted here also. So if you see here, 5 elements are there. And if you don't want to do convolution in frames, if you want to do the entire 2 frames together, like how many are there elements? These are 4 elements, these are 4 elements, 8 elements are there. Filter coefficients is 2. So output will be of length how much? Like what I'm saying is 4 plus first frame 4 plus 4 is equal to 8 samples are there. This we are convolving with 2 samples of 2 filter coefficients. Okay, 2 filter coefficients. Now output size will be how much? 8 plus 2 minus 1, which is equal to 9. So I have pre-computed the output. So these are the 9 values. So now using delay line we will try to compute this. So for that we have to see the code. Like if you see the code here, FIR filter code is this one. So it is taking parameters like input frame, it is taking input frame pointer, coefficient pointer it is taking, output pointer it is taking, number of filter coefficients. In our case this is 2 will pass here. This filter is 2 is right. 2 will pass here, and frame size is 4 in our case. 4 will pass here. So now the first when it enters into the FIR filter, first we have to see here. So this is the while loop. Here this is the input signal that we are reading. So this signal, every time we are reading frame size of the data. So frame size float values we are reading. So input. So this will be 4 values will be read here. So in will have 4 values. So now we will call the FIR filter with these 4 values. FIR filter will produce the 4 output values. So 4 outputs you will get. using this FIR filter. So now what is this FIR filter? First one that is coming is mem copy. Okay, mem copy from where to where? This is the destination, this is the source. So how much size? Frame size. So 4, frame size 4 in our case. So 4 elements we are copying. From where? From input buffer to delay line, but not delay line, not from the initial 0 we are not put here. This is not 0, but we are using number of filter coefficient -1, which is in our case 2 here. So 2 minus 1, 1. So one location we will be copying entire frame, 4 size frame we are copying. So that's what we are doing here. So first step is, so if you see here, so first step we have copied the entire first frame, 1, 2, 3, 4, this is the first frame. We have copied the entire first frame here. So this one will be 0, this one will remain 0. Now next what we are doing? This for loop we are doing for frame size. So like frame size is 4, for 4 times you are iterating, and then each output you are calculating, 4 outputs you will get. So in the for loop initial first time what you are doing, coefficient is equal to coefficient pointer. So coefficients I am initializing to the initial this pointer, and then delay line is what? This is 2 in our case, 2 minus 1, 1 will come, n will be 0 initially. So this will point to one location. So that's what I am showing here. This is pointing to one, this is a 0 location, this is 1, 2, 3, 4, these are locations. This is pointing to one location. Now for your convenience I have put the filter coefficients written here. So 1, 2 I have written here. If you see here what is happening inside, this is the loop. I told you that for each output calculation we will do m multiplications. M multiplication means here m is 2. 2 multiplications we will do. 1 multiplication is this, again second multiplication will come after, again the loop will go for second time, second multiplication, and then 2 additions will happen. Okay, thus input pointer is going minus minus and coefficient is going plus plus. So what does that means is, so first this is pointing here, right? Next it will point here, and then this multiplication will happen. So first this multiplication will happen for k is equal to 0. So k is this one only. K is equal to 0 case, first this multiplication will happen, this multiplication, that is what I am showing here. Next k is equal to 1 case, this coefficient will increase and this one will decrease. So what it will be, this one will decrease, so it will come here, 0th location it will come, coefficient will increase, so this 2 will be the 1. So that's the case. So 1 into 1, 2 into 0, so 1. So you got the first output. So this is the first output. So next what? Next is what? Next the for loop will this inner loop has been executed, then output has been stored. Now 1 has come. Now again you will go here. So next what? Next to n will become 1. So this is already 1. This again it is 1. So 2. So next it will point to 2. So 2 location will point. Again the same story will repeat. So 1 into 2, k for k is equal to 0, 1 into 2 will be multiplied. Plus for k is equal to 1, 1 into 2, 2 into 1 will be multiplied, and then the answer will be 4. This output we got. Next it will move here. Again the same story. 1 into 3 and 2 into 2 is 7. We got this output. Okay. Next it will move here. 1 into 2, 1 into 4, 2 into 3. So all 4 outputs we got. So outer loop is for length 4. Thus 4 outputs we have calculated. Now this particular thing we have to execute. So what is this saying? Delay line 0. Delay line 0 means what? This one. Here we have to copy something. How much is the copy length? Number of filter coefficients -1. Now I guess this is 2. So 1 copy we will make. So at the beginning we will make the frame size copy, that is 4 copies. At the end we will make 1 copy, that is filter coefficient -1 copy. So this in our case this is 2. So 2 minus 1, 1 copy we will make. From where? Delay line frame size 4. So 4 is this one. So this is 0. This is 0 location, 1 location, 2 location, 3 location, 4 location. This 4 will be copied to here. That's the case. That's what you have to do. So if you see here, this is the delay line state. Now we will copy 4 to here. Okay, that's what we did. Next what happens, this entire function has been executed. This last one is over. So now it will come here, it will write the output file of 4 values, it will write into the output file. Again the value will go, next frame it will read. Again it will call the FIR filter with the next frame. Again the story repeats. So when the FIR filter is entered, the first 4 values you have to copy. So where you have to copy? From this location 4 values like 5, 6, 7, 8 will come here. So that's what you are doing. 5, 6, 7, 8 have come here. Now again the same story will repeat. The for loop you have to execute, right? The same story will repeat. So it will point to one location first, and then 1 into 5 will do, and 2 into 4 will do. 13 we got this output. And again the same thing. It will go ahead, and then 16 we got. Then 19 will get. 19 and 19. Then 22 will get. Now all 8 values you got. Now next there is no frame. Okay. There is no frame. Now what you will do, we can assume that the next frame is all zeros. Okay, because we convolution output has 9 outputs, but we have only calculated 8. So next one also we have to calculate. So for that we will take next frame to be all zeros. So what happens is, so first this is the state of the data line. Now this mem copy we have to do, right? This one we have to do. So that one we will do now. So what happens is this 8 will go here. So that's what is happening here. 8 has come here. Now this entire thing will fill with zeros. Next one we don't have, right? So we'll fill with zeros. Again the same story will repeat. So 1 into 2, 2 into 8, so 16. This is what this value. So even further if you want to do also, all zeros are there. Zeros only will come. Okay. So that's about this entire convolution output we have got now. So that's how the data line we use and do the FIR filter implementation. So this is one way. So next we will see about the overlap and add method. Overlap and add method, what we are doing is, if you see here the figure. So for this case, let's assume that H, the filter coefficient are m plus 1 for the overlap and add case. Okay. So we will take block of length L. Okay. And filter coefficient is m plus 1. So what I meant to say is, so our block is of length L, and our filter coefficient is length m plus 1. So output will be of length m plus 1 minus 1. So that is equal to L plus m. Okay. L plus m is the length of the output. So linear convolution output is length this much. So what you will do here is, I'll take block L and do a linear convolution with this m plus 1. So what you will do, so if I want to use FFT, what you will do, this L we will make it as L plus m. So means m zeros will append. This m plus 1 will make it as L plus m again. So how many zeros will come? L plus m minus m minus 1. So that comes out to be L minus 1 zeros we have to put, pad it. For first one m zeros we have to pad, the second one L minus 1 zeros will pad. Both of them will make L plus m. Take the FFT of the first block of x with this one, and the FFT of this. Element wise we'll multiply the FFT, and then we take the inverse FFT, we'll get this one, y naught, this L plus m size. But the problem is, these m values are there, right? They are having only partial convolution. What I meant to say is, so if you see here, for calculation of 13, what was needed? Future value was needed. Future frames value was needed. Okay. So this 13 was there, right? This 13. This is for example, this is say 4 is the size and 2 is this one. So what will be the output size for this frame? 4 size and 2 is this one. So 4 plus 2 is 6 minus 1, 5 is the size. So for this output to calculate, we needed the next frames 5 we needed, but that was not available. Okay. So when we are doing here, the same thing is also here. So when you are doing for the up to L, it will be correct, but after L the one sample is there, right? In our case m was 2, so one sample will be having only partial sum will be calculated. Like what is this? What I am saying is, this is there, right? So 2 into 4 will only be available with us. This 5 into this thing will not be available. So we will make it this, we assume this all to be zeros. So we only 2 into 4 will be available. This 1 into 5 will come from the next this thing. So next this one will do, this one will do convolution with this one, right? From that we will get the 1 into 5. That we will add to this, so we'll get the total complete convolution. That's what we are doing in overlap and add method. So each block we will process separately. So one advantage we can take from here is, so this block is separately we are processing, this block is separately we are processing, right? So like we can run it, we can run parallelly. So like this block, you can completely get these two blocks together. We can get two blocks out, input, buffer them, and then run this parallelly in one thread and run this one in another thread, and then combine. At this point we have to combine them. That's all. That then we'll get the complete convolution. So like what is the advantage is, so we, instead of processing one after the another, we are processing parallelly. So that's in that sense some time will be reduced. So that's one kind of optimization is about that we are doing. So that's about overlap and add method. Next we will see about overlap and save method. Before we see overlap and save method, we have to understand circular convolution. So what circular convolution is, we have to understand. So like circular convolution equation, if you see, this is the equation of the circular convolution. This is a mod n is there here. So n is the size that you are taking as the this circular convolution size. So output length will also be of size n. Extra terms wraparound added at the beginning of the output. So what this means is, you will see with an example. So here n we are taking as 4. In overlap and save method, we have to take n to be greater than m. So it is 3 here, we are taking 4, which is greater than 3. So it's okay, we can take just 4. So now what happens is, if you see here, linear convolution I have pre-computed and put it here. This is the linear convolution output. So now when you do the circular convolution, this equation we are doing, right? This equation we will be implementing. Okay. So y of 0 will come like x of 0. So k will m will go from 0 to m minus 1, n minus 1. So k is 0 case, k 1 case, m 1 case, m 2 case, m 3 case. Okay. All these things are put. So x of 0 is almost 1. 1 into h of 0 is 1. So that I have put. Then x of 1 into h of 0 minus 1. Minus 1 means mod n we are doing it, plus 4 we have to do. So 3 will come. At 3 location there is nothing like 0, 1, 2, 3, nothing is there. So I put 0. Next x of 2 into h of minus 2. So minus 2 plus 4 is 2. 2 is what? 0, 1, 2, 1. So 1 I have put. Minus 3 plus 4 is 1. So 1 is 1. So that I have put. So we got 8. Similarly other things I have calculated. If you see here, the first two outputs are corrupted. Okay. 1, 3 I was supposed to get, but I got 8 and 7 in circular convolution. The remaining two are correct. 6 and 9 are correct. Okay. So what happens is, m minus 1, that is two values, initial two values will be corrected. Remaining n minus 1, remaining two n minus m, whatever may be the case, that one will be correct. So in our case, n minus m minus 1, that is 2, these two values are correct. So that's how overlap and save method will exploit this thing. So if you see here, the same thing I have shown here, the thing, and y linear plus k plus n. So this is linear convolution. We are how the overlap is happening, that's what I have shown here. So like 1 plus 7 it is adding here. So this 1 is there, right? This 7 is coming and adding here. That's what I have shown here. This 4, again this 4 is coming and added to this 3. That's what is happening here. And remaining all, nothing will come, because y k plus n. So k is how much? K is 2. 2 plus 4 is 6. 6 there is no value here. How many values are there? 0, 1, 2, 3, 4, 5 are there. 6 there is no value. So nothing will come here. So these values will be clean. So nothing to be added to them. So this will be clean. So that's the idea. The idea of overlap and save method. So if you see here, we'll take a length n. This n should be greater than. So again here h is m plus 1. M plus 1 is the filter coefficient length. So that is the case, not m plus 1 is the filter length. So n should be greater than m plus 1. So we will take this and then I'll take n block and then take the FFT, and m plus 1 we will append how many zeros? M plus 1 means you have to make it n plus 1 is the 1, n minus m minus 1. These many zeros we have to append to the filter coefficient and make it of size n. Make the size n, and then you take the FFT of this block, this entire block, and the FFT of the filter, and then element wise multiply, and then take the inverse FFT. So when you take the inverse FFT, what happens? The first m values will be corrupted, remaining n minus m. So m plus 1, right? So m plus 1 minus 1, so m values will be corrupted. Okay. So n minus m will be correct. So those you will take. So next one, if you put this block m here, these values will be corrupted, right? So the correct values have already got here from the previous frame. So anyway, if you put overlap here, these will be corrupted. Anyway, these values are available here. From here we can take. So you can concatenate these two things. So that's the idea. So these m values will be anyway corrupted. Let us overlap with the previous one. We had the correct values in the previous one itself. So let us throw these values and then concatenate the next values to this. So that's the overlap and save method. So that's about this. So next we will see about float to fixed conversion. So like this is okay. Floating point. If you see floating point, there will be one sign bit and 8 exponent bits, and mantis are 23 bits are there. Okay. So what happens is we have to handle both exponent and mantis separately. Exponent and mantis are separately. So the two functional units will be needed for this. In the case of int or short, there will be only one unit is needed. In the case of floating point, 2 units are needed to handle exponent and mantis separately. So that's why the floating point is very high cycles compared to integer or short kind of data type case. This one. So and why we go for float is dynamic range is very huge. So we don't have to worry. Like very small number like 0.0001, like that small number also floating point can represent, and even bigger number like 10 to the power of 20 or 10 to the power of 30. So that numbers also it can represent. So we don't have to worry about. So when you do any algorithm, any FFT or anything that we did, right? So initially, if you see here, this one only you take, for example. So initially these were up to 8 only. This was the range. So this was the range up to 2 was the range, but the output has gone up to 22. So if you see here, so fixed point, we have to take care of these things. We have to take care of these things ourselves. But in floating point, this is taken care because the dynamic range can be anything. So if at all this number is very small, say for example 0.0001, and this is coming to be 10 to the power 20, we don't have to worry about anything. The algorithm we can implement floating point, and it will take care of. It will represent this number also, this small numbers also, this numbers also it can represent. So that's the idea. So floating point can represent all the numbers. That's why we implement algorithms in floating point. Easily we can implement them, and then after that we will convert them into fixed point, and then for sanity check whether our fixed point code is working or not, we will compare the output of the fixed point with the floating point. That you will see now. So motivation for fixed point is low power. So anyway, we will be doing integers like the integer, short, and all is the thing in the floating in the fixed point. So the computation will be less. So the power consumption also will be very less. So a small memory fund like a fixed point, we can represent either 8-bit, 16-bit, 30-bit, anything we can take. So the number of bytes, 8 bits is 1 byte only is there. 16-bit, 2 bytes are there. But floating will, if you say in animation, there is 4 bytes are needed. So memory is also reduced in the case when you use fixed point. And faster execution. Faster execution in the sense that faster execution means I told you, right, floating point will need two functionalities for handling both mantis and exponent. But in the case of fixed point, only 1 unit, and integer multiplications will be there, integer additions will be there. So that's the idea. So hardware limitations. So hardware limitations means some DSPs don't have floating point unit at all. So in those cases, we have to convert our code to fixed point. We cannot put a floating point count on a hardware which doesn't have a floating point unit. So it will not work. So some wrong outputs it will generate like. So in those cases, fixed point is definitely needed. So if you see here this figure, so this is a uniform quantizer figure. This is a mid-rise and this is mid-thread. So in the case of fixed point, we will be going with mid thread. So why we round the values? So it is between minus 0.5 and 0.5, we'll round it to 0. 0.5 and 1, we will round it to 1. Minus 0.5 minus 1, round it to minus 1. So that's how we'll do in case of fixed point. Okay. So fixed point representation, like one sign bit will be there, m range bits will be there, and n fractional bits will be there. So this is the Q format that we will be showing here. So what that means is, you will see now. So this is the Q formats B. So if you see this, what is this? This is nothing but 2's complement representation only. This is 2's complement representation of a number. Okay. So we are dividing that by 2 power b. So b is the Q factor. So what will be the range? So if you do here, so if you see here, if you put in this, if this is 16 bit, the smallest number that we can represent is this is the smallest number. This is the smallest number in smallest 16 bit number is this one. What is the largest 16 bit number? Largest 16 bit number is 0x7. If I have put it in hexadecimal, but if you want to see them in this thing, we can see. So this is nothing but this will be like I'll show you what will be that number is 2 power 15 is how much. So this is the case. So this is how much. So this is equivalent to minus this thing, and this is equivalent to 7. Minus 1 we have to do, because 0 is also we have to account, in between 0 will be there, right? So from here to here, this is the number. This number we are this is the range. So this is the number, this is the range of the short case. From this number to this number you will represent. Okay. So that we are dividing by 2 power b. So this will be the range of the output. If you do the calculation, you will get this. This is the range. So if x is the number, if you divide by 2 power b, this will be the range. 2 power n minus 1 by n is in the case 16. 16 minus 1 b, and this is the one. So let us see the example. So if it is a Q1.0.15 format, then the range is 2 power 0. If you see here, 16 is this one, 16 minus 1, 15, b is 15, 15 minus 15, so this is 0 entirely. So that's what we are showing. So Q format is written like this, 1.0.15. So minus 2 power 0 to 2 power 0 minus 2 power 15, 2 power minus 15. This is the range. So if the number falls in this range, we can safely represent using this Q format. Okay. If the number is going out of this range, then we have to worry. So that's what I said, right? That's what I said, right? So if you see here, this output rate. So this is 8. This is up to 8 it is going. But this output is going up to 22. So the same Q format, if you see coefficient, we can represent with what Q format, like coefficient you can represent with Q 1.1.14 format. Okay. So 2 is the one, right? 2 power 1 is 1. So you can represent with this one. Then input, what you can represent with input okay. So input you will represent with what? Input is up to 8 it is going, right? So we have to represent it with Q1 dot 3 dot 2 power 3 is 8, so 1.3 dot 12. So this all things should add up to 16. So if you see here, this is 15, 16. So this is also adding up to 16. Okay. So output Q format is what? Output Q format should be what? Output should be, like, it is going up to 22. So its Q format is 1 is for sign bit, and there one 22 up to 22 it is going. So like 22 nearest 2 power is 2 2 power 32 is, I think 32 is the one, 16 after that 32, 32 only. So 2 power 5 is this thing, and then 10. So that's how it is at the Q formats. Okay, so floating point you don't have to worry about all these things. So okay, so but in fixed point you have to worry about all these things. Okay, that's about this. So where are we? So this is the Q format. So this is the range that is there. So each range we have to, so that's the case. So now we will represent this number. So this number is, we can use Q 1.0.15 because 2 power 0 is 1. 2 power 0 is 1, minus 1 to 1 minus 2 power minus 15. So this is in that range only. So when, how to convert this float value into integer value? So we multiply with 2 power 15 and then we round. That's what we showed here, right? Mid-rise, mid-thread. That's what we are doing here. Same thing we are doing here. So where is that? Okay, this one. So that's the case. Now if you want to convert this back into float, then we have to divide by 2 power 15. Okay, so this one to divide by 2 power 15. So if you see here, you got this number. So what did we start with? We started with this one. So this entire this thing is quantization error. We cannot avoid it. Entire this thing is quantization error. So we cannot represent the entirely exactly this number. So some quantization error will be there. Similarly, the other number also there will be some quantization error. If you see this one divided by 2 power 15, the same thing will happen. So another representation also I have shown here, like so 2.48. So this is more than 2. So more than 2. So 2 power 2, 4 is needed. Range bits are needed. 1 is for sign bit. Remaining are fraction bit. So how will you convert this to fixed point? You will round it. 2.4897 into 2 power 13. This number will multiply, and then this is the number we will get. Okay. Similarly, the example 2 case, this is the minus 5. This is more than 4. So 8 is the one. So 2 cube 8. So range bits are 3. 1 is the sign bit. Precision bits are 12. So how will you round it? You will multiply with 2 power 12. How will you make it into integer? You multiply with 2 power 12 and round it. So after that, all are integer arithmetic only we will be doing. So I have prepared a small demo. I will show it now. Okay, clear outputs. So if you see here, I have written a function show binary. Number I will pass, and the number of bits I want to this number to be represented. I will pass the number of bits also, and it will represent it. So we are going with 4 bits short toy problem. So one is Q 1.0.3 format. So this will represent numbers from minus 1 to, this is nothing but 1 by 2 power 3. So this 3 is coming from this. So this is 2 power 0 minus 1 will become 1, 2 power 0 minus 2 power 1 by 3. This is nothing but 0.125. Okay, that's the case. So similarly, so this is the other format is Q 1.2 format. So this will represent number from, this is this is the one that, so range is 2 power 2, 2 power 1. So 2 minus 2 to 2 to, so this will be like, this is nothing but 1 by 2 power 2. That is nothing but 0.25. Okay. So now what I am doing is I am printing the levels. So like various levels of these two floating point for these two fixed point formats. So like so if you see here, this is for the first case 1.0.3. So it will start from minus 1 and then go up to 0.875. The second one will start from minus 2 and go up to 1.75. So total how many levels? 16 levels will be there. 4 is this thing, right? 4 bits, right? Total 16 levels will be there. So similarly, I have put the binary format. So if you see here, okay. So this is the binary format. So in both the Q format case, this -8, in the first format case it will be -1, that is 1.0.3 case it will be -1, in the 1.2 case it will be -2. So that's the case. -7 will be like, that's how we will convert that. This number we will multiply with 2 power 2 in this case, and then this number in the case 2 power 3, and then round it. So that's what we will do. So that's the case. So these are the numbers. These numbers will under the hood, these numbers represent different things. So once finally when we are converting into float, we have to be very careful with the Q format. If you mess up the Q format, then outputs will be very wrong. So the output will be like, if you are supposed to divide by this number by 2 power 3, for dividing by 2 power 4, the output will go very wrong. So it will, the outputs, the RMSE that I told you, right, will compare between the fixed point and the floating point. It will be like very huge. So the numbers will be like, we are almost making it half, because 2 power 3 we have to dividing by 2 power 4. So we have to be very careful with the Q formats. So at every stage of the multiplication, addition, all those things, various Q formats, how it is changing. So all those things you have to keep track of. That's why fixed point implementation is very tedious. The very reason is because you have to keep track of how the Q formats are changing. So whether it will go outside, if I put a Q format, is it going outside the Q format or not? If it is going, I might have to increase the range bits. So all those things we have to take care. So that's the thing. Next I will run this. Next let's represent this number. Okay, this is number in format 1 case and format 2 case. So if you see here, format 1 it has represented as -0.125, and format 2 case it is represented as 0. So y means, so this number can be very efficiently represented by this format. Okay, this format, if you use it, we can represent it, but thing is the precision will be lost, because we are using precision only 2 bits we are using. Okay, here 3 bits we are using. Okay, so that's the reason why in the format 1 it has given as -0.125. If you see the quantization error here, it is huge. This is huge, but here the quantization error is less. So if I give some other number, like for example 0.7, then, and both are representing as same, then I give as 1 point. So now this is going outside for this format 1. If format 1 is from -1 to 1 minus 0.125, right? So this is more than that. So now see what happens. So it has rounded it to the highest negative value, that is -1. Okay, so this is the binary representation. Okay, so this has represented as -1.75. Okay, so here the quantization noise is very high, because this is the number which is outside of this range. That's why this quantization number error is very high. So -1 minus this one will be 0.7 something will come quantization error, but here it is less, because we are using a number which is outside its range. So the quantization will be very huge. So one more thing we have to see here. If you see here, now I am using 16 format. So now forget about this example that we have taken. Now we are using this format, 1.2.13 format. So the number that we represent is -4 to 2 power -13. So this is the range that you can represent. Now I am giving a number which is out of this range. Okay, so now what happens, let's see. So for a fixed point number, it has represented as highest positive number it has represented. So that's why it has represented, because I have clipped it. So if I remove clip, here I have removed clip. So if I run this here, what happens, you see, it has represented as negative number, negative -191. Here it has represented as biggest number in the short case. So that's how it's short, right? 32,767, but has become negative. This is what is called overflow. So here we have saturated it. So if at all it is going beyond the maximum number, we will saturate it to the maximum number. If you don't do it, then it will overflow, and the positive numbers will become negative and negative numbers become positive. If you give it minus this thing, run this, now it has become positive, if you see here. So overflow is bad in the case of fixed point implementation, because negative numbers will become positive and positive numbers will become negative. So we have to be very careful. We have to use saturation. Like if it is going beyond the maximum number that can be represented, we will saturate it to the maximum number. If it is going below the minimum number which is represented, we will saturate it to the minimum number. So that's how we have to do. That's the clip that I have implemented here. That's saturation. So that's about this. Now what we can do is, so precision range instead of, okay, this, okay. So now addition and subtraction. So like addition and subtraction, how will you do in Q format? So it is straightforward. Both have to be in the same Q format. Okay. So now if you see here, this, let's this bit 2, that's 3. Okay. Now if you want to add this Q formats, Q1.2.13 and Q1.3.13, 3.12, I think this will be 12. Okay. So if you add up all these numbers, it is coming to 16. Okay. 16. Okay. Now it is correct. Okay. So if you want to add these two numbers, then will you convert Q.1.2.13 to Q1.3.12 or Q1.3.12 to Q1.2.13? So which one you will do? The answer is whichever is having the highest range bits, because there will be the biggest number, right? So we have to convert this to this one. So how will you convert this to this format? So you will right shift this by 1. So then it will become like 3.12 format. So now the problem is, previously what was it? 2.13. 13 means there were precision bits were more, but we have made it as 3.12. One precision bit we have lost. Okay. So this is we are losing precision, right? So because that's, if you don't want to lose precision, then what we have to do is, we have to typecast these two things into int. So now then we will get 16 range bits additional. So this will become 16, means this will become 18. This will become 19. Okay, we have typecast it. So like we got additional bits, right? Additional 16 bits we will get. So those will add to the range. Now we can left shift this one. So there is no problem with this. Left shift, even if left shift 19 is the range bits. Previously it was this was how much? This was 3, right? So 19 range bits are right. So we can left shift this. There is no problem. So when you left shift this will become 13 and this will become 18. And now we can add them. So we can keep them in 30-bit. So when at the end we may need to convert it back to short again. At the end with saturation. Okay. Without saturation, if you do, then I think it will overflow and negative numbers will become positive and positive numbers will become negative. So that's one problem will be there. So when you are converting it back to short, we may have to take care of the saturation. So without that, it might overflow. So then multiplication is, if you have Q1.m.n format and Q1.m.n format, the output format will be Q. So like if 16 bits is there, 16 bit into 16 bit, we need 32 bits to hold the output. So output will be of Q2.27 bits will come, 2m will be the range bits, 2n is the precision bits. So now we will see the range and precision trade-offs. So like if we increase the fractional bits, then range bits will suffer. If we increase the range bits, fractional bit suffers. So what I meant to say is, so if you see here, if you want to increase the precision, this is the case, this is the Q format, Q1.2.13, the precision bits are only 13. Okay. So if you want to increase the precision bits, then you have to increase the number of bits. So if this is 32-bit case, so like 1, 2 and 29. 29 bits for precision we have got. Now the precision is more. So like we can represent numbers more accurately, like float numbers like more accurately compared to these numbers. The quantization error will be less in the case of this one. Okay, but the range is same, -2 to 2 minus 2 to the power of -13 is this one, is minus 2 to 2 minus 2 to the power of minus 29 is this one. So the only thing is quantization error will be less in the case of this one because you are using 32 bits here, and here it will be less, quantization error will be more here because you are using 16 bit. So that's the one idea. So if you, so that's the case, if you increase the range bits, like 3, then this will suffer, precision bits will suffer. So if you want to decrease the range bits, if you want to increase the precision bits, then range bits will suffer. So there is a trade-off. So we have to take care of that depending on the algorithm, like what we need. If more precision is needed, then I think the more precision is needed, then we need to go for higher number of bits. If a range we cannot reduce and increase the precision bits, in those cases we have to go for higher number of bits, 32 bits we have to go. That's the idea. So next is like if you see here, the same example I will take now, the same example that you took, right? So that one we will take. Where is that? So if you see here, so this is this Q formats, if you want to fix for these things, filter coefficients, and then for the frame size. So now how will you fix the Q formats? So like if the coefficients are, say for example, like this, h of 0, h of 0 and h of 1 are the coefficients up to h of m-1, and if you take the abs of each one of them and then add all of them, that is the number which we can get, maximum number that we can get in the accumulation case. When you are multiplying like h of 0 into x of 0, h of 1 into x of 1, like the multiplications you will do, right? Like I told you, right, in case of calculation of one output, you will do m multiplications and m-1 additions. So that's what I am doing. So this is the maximum number that can come, okay, and x max is the maximum one. This is the maximum number that we have to represent, y of n, okay. So like that you have to take care. So if you see here, we can't take this Q format as, if you see here, if you want to fix the Q format of this coefficient Q format, we cannot fix it as a Q 1.2 is the one, right? So 2 is 1 we can take, and then 14 we can't fix like Q.1.14 because we have to add all these ones, like add all these ones. 3 is coming, 3 is greater than 2, so the next nearest number is 4. So 2 this one and 13 this one we have to keep. That format we have to take, okay, because I told you, right, as I told you, because we are multiplying and accumulating. So the maximum case will come when you take the abs of all the coefficients and then add. So here the abs of all coefficients, abs of 1 is 1, abs of 2 is 2, all of them if you add them it is coming to 3. So that one we have to represent in Q format. So that comes out to be Q1.2.13, okay. So input is what? Input maximum we can take. Input Q format we can take it as Q1.8 is the maximum, so it is a 2 cube is 8, so 3.12 format is this thing. So when you multiply these two numbers, so output will be what? Output Q format will be what? Output Q format will be, when you multiply these two numbers, two range bits will come, two sign bits will come, and this and this 2 plus 3 will come out to 2 plus 3 will come out to be 5. Okay. 5, and then these range bits, if you add them, then it comes out to be like 25. So if you add all these numbers, it will come to 32, okay. So 32 bits are needed. When you multiply two 16-bit numbers, the output will be 32 bit, okay. Now when you want to convert it back to, so if you see here 2 power 5, 32, so 22 is in that range only, so we can represent this number. Previously if you had gone only for Q 1.12, because this is up to 2 only, right, we don't need up to 2 case, 2 power 2 is not needed, then the Q format will be 4 dot something, 4.24 will come, output Q format, and this maximum number that you can represent with this is 2 power 4 is 16. These numbers, these 19 and 22 will be clipped to the maximum. 16 they will come, so we can't represent them correctly. So what I meant to say is, so if you see here where we calculated those values, so where we calculated, so this is 22. Okay, now this one, what is the Q format what you have set? 18th slide. Okay, so Q format is 12. So this one we will multiply with, this one we will multiply with 2 power 12, and 8 will multiply with 2 power what is the Q format for that? What is the Q format for our input? 12. Okay, 2 power 12 is, this is, I think this is wrong. I think 2 power 14. I think actually, what is this? One is this is 2 power 14. So now 18th slide. So this will be 14, and this will be 2 power 13. That's one only, right? Input Q format was 2 power 12. Okay, 2 power 12 is the input Q format. So like this it will come. So this will not be representable in 32-bit. That's what I want to say. I want to emphasize. So if you say here 2 power 14, and this is into 2 power 12. So if you see this entire number, we cannot represent in float in a 32-bit. That's what I want to say. So if you see here, if you take this entire thing, if you calculate this, use the calculator. If you see 1 and 2 power 14, 2 power 14 plus, and then what is the number? 8 into 2 power 12. Okay, 8 into 2 power 12. This is one thing, plus, then what? Oh, these two are multiplied. Okay, we copy this. I think we can copy this entire thing here. I think this entire thing I'll copy and then give it here for 12. Okay, then what is the output? This is the output. Okay, if we take this and go to programmers mode, and then quad, what is there? Decimal. Okay, we paste it here. If you see this number, if you see, this is the 4 bits, 8, right? Then this is 16, this is 32. What is about 4, 4, 8, 12, 16, 16, then 20, 24, 24, 28, 28, 32. Okay. This number is representable in 32. So what has become this number? Okay, what is this? Should not be representable in 32-bit. Something wrong here. Let's check what has happened. So 1 into 2 power 22 will come. 22. So it is representable in 32-bit in this case. So I don't know why, how come it has been representable in 32-bit case. So what is the output Q format here? What will be the output Q format here? The output Q format will be Q1.14 is this one, Q3.12 is this one. So output will be like 21.4.26 is the output Q format. Okay. So 26 is the output Q format. So the maximum number that can be represented is 2 power 4, 16 only. The 22 should not be representable. So how come this has been representable? I'm not able to get. So what is happening is 1 into 2 power 14, 2 into 2 power 14, 8 into 2 power 12, 12 power 12, right? Okay. something wrong is going. So let's do each one separately. So this one I will take and then add here. I will go into scientific calculator mode and then I paste it here. What is the output? This is the output plus. I'll start a bracket here and then I copy the next thing. This thing I copy and then I close the bracket. So this equal to this much. Entire thing I will copy. I'll go into programmer mode and then decimal case quad bit. I think 64-bit is not representable here. That's the reason why it is not showing. So let's use our this thing, our VS cursor. I will open cursor. I will open. .vm, we will come here now. I'll pause this video and then again I will do it. So what I meant was, so if you take this number, so like what was the Q format that you have set, like Q1 dot, so 2 is the number, so to 1.15, and for this the 8 was the maximum number, so we have set it as 3. So this output Q format will be this one. So now what I was doing was, I was doing this one, so I am converting this float value to fixed point, so I have to multiply 2 power 14. This one, if you want to convert into fixed point, I have to multiply 2 power 12. So that's the thing. So entire thing I will take now, entire thing I am taking now. So this thing I will take and then I copy paste here, so I get this value. Now if you see here, the output Q format will have like 2 sign bits. We have to shift left now, this one. Okay, so this one, if you take this thing and then go here and go to programmers mode and then you paste here, so this is this much. Now we have to shift left by 1, so to in order to remove 1 sign bit. So when I shift left by 1, so what happens? So this becomes negative. If you see here, upper bit is become 1, so it has become negative. Okay, so that's the thing. So it has become negative. Actually this is double word we have to keep, I think. Okay, double word you will keep. So double word if you keep, see it has become negative now. Okay, so that's the idea. So like that is the reason why we we both, if you add absolute value of 1, absolute value of 2, and then add, then 3 will become, this will become 2, this will become like 2 plus 3 is 5 will become. Now the equation will change. So this is how much? This is 15, 2 not 15, this is 2 dot 13 it will become, and this one is same only. So okay, so now this will become 13, this will become 13. If I do the math, here in scientific calculator and then I see the output, so this is the output. This one I copy and then go to programmers mode and then I paste here, and if I shift left also, double word only I am keeping. So if I shift left by 1, this will not go into negative, so this is positive only. So this is the number which we got previously. When we shift left, then it has become negative. Now this one we have to, this one if you copy this and then go to scientific, and then this one we have to divide by what? Divide by, what is this, output Q format? Output Q format will be 25, I think. 25 will be, it's a 13 plus 12 is 25. Output Q format, sorry. Output Q format is 25. So 2 power 25 we have to divide. Okay, so 2 power 25 if I divide, this will come out, okay, 44. So we have left shift right, then we have to divide by 2, so that will come to 22. So now the answer is correct. So actually we have left shift right, so that's why one right shift we have to do. Okay, so that's how it is there. So the absolute value of these coefficients we have to take to form the Q format. So now if you don't want to take that, if you see the example here, so if you see, I have given the example here. So this is the coefficient which are generated by the MATLAB Python tools. So the maximum coefficient that has come is 2.78 something it is coming. Minimum is this one. So the absolute sum of all the coefficients is this much. So what should be the Q format of this FIR filter coefficient? So 24 is closer to 32, so 1.5 dot something you have to take. So that's what you will do now. So if you see here, so VS provide FIR filter, and then I will open the solution. So if you see here, so this is a FIR filter that we have implemented, right, that I have shown in floating point, that I am implementing in fixed point. So what happens is this become like intertype is nothing but intertype is word 16, that it is short. Short is the input type is short. Coefficient type also I have put it as word 16 short, and then output type also I have put it as short. Okay, number of filter coefficient, all those things are okay. So delay line, everything will be like, now integers will be there. Now the multiplication I have put one function here. So this function what it does is, this function if you see, intermediate type E, it will typecast the numbers to. Intermediate type is what? Word 64, that is long is the word 64 bit word it will convert, multiply them and then add to this sum and then give the output. So that's what it is doing. So instead of 16 bit, these are 16 bit, right? These two are 16 bit. It is typecasting them into 64 bit and then multiplying, and then so there will not be any overflow in those cases. So because we are typecasting into 64 bit, so two 16 bit number multiplication will give output as 32 bit, but we are using 64 bit. So there will the result will sufficiently fit into it. So we will add them and then get the result. So that's how we are doing. So output you will get, then output we are into precision bits is, this is 15. So output we need in 16 bit format, right? So like this if you multiply two 16 bit numbers, the output will be 32 bit. Okay, so 32 bit will be the output. So from that top 16 bits you need, so we are rounding and then taking the top 16 bits. So we are shift writing by 15 bits, we are shift right we are doing, because the two sign bits will come, right? One sign bit we don't need to take, so that's why 15 we are doing. If we do 16 bit left shift, right shift, then two sign bits also will come. So just right shift by 15, if you do, one sign bit only will come in the output. And then again we are typecasting the short. So that will, so to top bits we are taking, but also what we are taking is, so what I meant to say is, top bits we are taking, so 31 to 0 the 30 bit number. From that 31 and 30 are both sign bits. Okay, so both are sign bits, two sign bits will come. So from 30 to 16 we are taking. So how many will come? 30 to 16 means, so 30 minus 16, if you do that, 30 minus 16 plus 1. So this is not, so it's not this one. It should be like 15, I think. Up to 15 we have to take. Okay, then it will become 16 bits. 16 bits will come. So for this, what you have to do, this entire this thing we have to shift right by 15 we have to do. Then we will get 30 to 15 bits in the lower part of the this thing, and then when you convert into short, these bits will be taken. Okay, so that's the idea. 30 to 15 you will take. So these will be 16 bits will be there. So because 2 sign bits are there, right? 30 to 15 you will take, and then that's the reason why we are left shifting by 15. Okay, so 15 will be gone, and then the from 30 to 15 will be available in the lower bits of the 32 bit. Then when you convert into short, lower bits only will be picked, right? So the exact value will come. So that's the idea. So that's what we are doing here. So if you see here, so the range bit should be 5 for coefficient. Why we coefficient? Because the sum is coming to be 23, right? So the range bits has to be like the nearest one is 32. So 5 is this. So this one. So this should be 5 bits. And the input is I have checked maximum and minimum I have printed. So 3 is this thing is the range bits that is needed. So remaining all are precision bits. Okay. And for output, what will be the range bits? These two you have to add. 5 plus 3 is 8. Output will be like 8 is the range bits. Okay. So I am converting this to float again here. Fixed to float I am converting, and then writing into the output file. Okay, here. Okay. Output file here. And this is a floating point FIR folder. Here is the fixed point FIR folder. Okay. So that's the thing. This code we have already seen. So I don't want to explain it again. So we will directly run this. So if we run this, everything is okay. Now we are rounding and shift lifting. Then if you run this, it's running now. So it has given the output. Now let me close this. It is becoming slower, I think. So I will close this. We'll close. It is closed. Let me close this. So it's closed. Close anyway. Okay. Now it is closed now. Now what I have to do is I have to get the RMSE value. Floating point value already I have calculated. So if you see here, CD I will do into Python project, and then FIR filter. So I will call this. Now I have to set the environment. So sorry, I will first set the environment. So VNV /scripts /activate. So environment as well. Okay, what is that? Activate spelling is active. What is the product? /scripts activate. System cannot find the path. It is saying. We check VNV. Oh, okay. In Python only it is there. Okay. So if you see here, if you go here, cd python /FIR, and then I will set the environment VNV /scripts /activate. So now what I will do is Python I will give, and then calculate RMSE, one function I have written. So then I will give the first input is the Python generated output. A filtered signal is this one. Second output is the MSVC output that just now we have generated, right? So that is in VS projects /FIR filter, then out. So if you see here, output is written into what? Output is written into this buffer. This is the output. The same thing I am giving it here. So if you see here, this is the same thing I am giving here. So if you see here, this one will come out to be RMSE value will come out to be how much you will see now. Minus 40 something should be greater than minus, so minus 49 it is coming. So if you see here, this is the Python implementation output, this is the C implementation, this is the error between them. So the mean is this much, the maximum value is coming to be this much, maximum difference between them is coming to be this much. So this the signal 1 minus signal 2, that's what you are doing, and this is the error signal that you are printing here. So the RMSE value is coming out to be minus 49. So if we can improve on this, so what we can do is, so if you see here, we are doing what? We are typecasting it into 64-bit and then multiplying, right? So okay, so that's what we are doing. So like we have like 32-bit will be the output, but we are having 32-bit extra bits. So 63 to 0 are bits that are available, but we are using only from 31 to 0 only we are using. So like additional 32 bits we are not using it. Additional some 63 to 32 we are not using it. Now we will start using them. So what we will do is, so if you see here, this is this we can represent, these numbers we can represent with 2 power 3 like 2 power 2 like 2 power 3 like 8 we can represent, right? It is greater than 3 4 2 power 4 we can range bits 4 2 we can represent these things. So but we went for 5 range bits because the sum was this much, so that's why we went. Now we have some additional bits, right? So we will try to exploit them. So now what we will do is, we will make these range bits to be 2 now. Instead of 5 we'll make it 2. So the everything is correct only, this is same. Now what we will do is, we will make this to be, these things will comment. Now I will explain what I am doing. So now if I run this, so this is run. Now if you see the RMSE value again, if I calculate this, so same thing, same output. So it will be better than this. If you see here, minus 49 was the previous one. It is less than that, minus 52. This is even lesser. Okay. So we got better results. So what we did was, so now what we are, so now we know that, so the previously we kept it as 5 as the range bits for coefficient. So the result was in the 0 to 31. Now we have made it as 2, right? So it will extend into this thing now. The result will be now occupying like 31 to 0 it will occupy, but also here 32, 33, 34. So these numbers also it will occupy. Let it occupy because we have 64 bits, right? Let it occupy this range. Now at the end what you will do is, these 3 numbers plus here some 3 numbers we are taken. Here we will take 13 numbers from here. So that's what I am doing here. So what I am doing is 64 minus 32 minus 3 I am left shifting. So this, so what will happen is, this entire thing will go to the top, this entire this thing. So 34 to 31 will go into the top. After that what I am doing? After that I am doing left shift by 46. 46, why? We need 16-bit output, right? So like these things will be like 46. 46 how I got is, so if you see here, that upper 16 bits we need. So like how much we have to subtract, how much we have to right shift? So 64 minus 16 we have to do, 16 bits are needed, upper 16 bits are needed. So 48 is this thing. So 2 sign bits will be there, minus 1 we will do. So 47 will come. And then what is so this, so what is this upper this is thing is like 64 are there, upper 2 sign bits will be there, like 16 we need, so 15 we have to do. So like 49 is coming. Okay, what is this? So what I mean to say is 47 is the one that you will get. Why I am saying is, so 64 is there, right? 64 minus 16, it will come to 48. Minus 1 because we are doing this thing, right? We are doing 2 sign bits will be there, right? So that one we have to left shift by 1. So that's why minus 1 we are doing. So 47 is the case. So we have to round, means this should be 46. So 1 bit above we have to round. So rounding, what you will do, like if at all there is a bit here, you have to left shift. If at all there is a something like 1 0 1 1 something is there, if at all you have to left shift by 1, you have to round the here, right? This one we have to round. So we have to left shift this one by, right shift this one by 46 and then add 1 to that, and then left shift by 1, that then it will be correct. This is what we are doing, 46 and 47. So that's what I got. 47 I got, right? That is the way. So we are right shifting by 46 and then again by 1. So 47 is this one. So that's the idea. So we got better result. Now even better result we can get now. So what we can do is, instead of this one 16, we can make it as 32. The coefficient we can make as the precision bits will increase, right? Precision bits will increase. So let's keep this as 5 only. 5. So now what will be the case? This one is this one we will keep, and this one guard bits we are not using now, just precision bits we have increased. So now the coefficient is 32 bit. The output will be like output what will be the this thing, 32 into 32 plus 16 is the output, this thing. So 48 will be the number of bits. Okay, 48 output will be the number of bits. Now if you want the top 16 bits minus 16 we have to do, that will come to 32. So 32 we have to do, then 32 we can don't do because one sign bit will be there, right? But 2 sign bits will be there. So this will be 31 actually. So this will be 31. If you see now, if you run this, so okay, this is okay. Now you go here and then check the RMSE. Okay, so RMSE is very bad. So let's check what we did wrong. So this is, we will mess up with things. Okay, so we need top bits, right? So what is happening here? Top bits are needed. So the result will be 32 into 16 will be like, what is the 32 plus 16? It will occupy like 48 bits. 48 bits. From 48 bits we have to right shift by how much? You have to get the top 16 bits. Top 16 bits you want, if you want to get, what you will do? Minus 16 if you want to, 32 will come. So 31 is correct only. So why it is going wrong? Int type is 16. So 31 16. Okay, here this is the problem. Okay, so this one coefficient precision base I have to make it as 31 because that is the case, right? So that is the one we did made the mistake. So we'll run it again. So we got the result. Now we will calculate the RMSE. If you see now RMSE, so previously we got minus 49, now we got minus 52.53. So even better result we got. Now we will use this guard bits thing we will use now. Okay, so guard bits thing if you use, then we will make this 2. So this is 2 now. Then this one we have to check what we need to do. So this will have to comment out. So now the output will be of 48 size. So this one will be 32 will become 48 will become, and then this one is again 46 only we have to left shoot, so that don't change. So this is correct only, I think. Let's see. Should be run. We'll run this. So it says output has come. Now we'll check the RMSE. So no, there was no much difference was not there. So not much difference. 3.1. So the same thing has got. So there was no much difference. But in the case of 16-bit, when it was 16-bit, there was a lot of difference was there. Like 52 from minus 49, it has jumped to minus 52. So that's about this. So we have to be very careful with QMRs. Like I see, I messed up something here. So this 31 I forgot to change. So because of that, the entire result got wrong. So be very careful with Q formats when doing. So that's the idea. Thank you very much.